Hello everyone, my name is Tom Xu. I'm from the Australian National University. Today I would like to introduce you to our work Neural String Diagrams, a universal modeling language for categorical deep learning. This is developed by myself and my supervisor Yoshihiro Maruyama. Let me quickly outline this presentation. So first of all, I'll introduce some background information of category theory. Then I'll introduce our category theory approach to deep learning, then followed by the technical frameworks we use, which includes string diagram and Dagger compact category. In the end, I'll show some neural string diagrams for convolutional neural network and transformer neural network. So first of all, category theory. Category theory is an abstract mathematical modeling language to express various sorts of structures and their compositional relationships. And the key concept of category theory is the compositional relationships between structures. And different fields of science can share common categorical structures. I'll give some examples later on. Therefore, it gives a unifying perspective across sciences and facilitates transdisciplinary knowledge transfer between them. So there are some key characteristics of category theory. So it's about abstraction, and it's about compositional relationships, and it's about finding common structures. And I believe these are intrinsic to artificial general intelligence. So simply speaking, a category C is an abstract structure of objects and arrows, and mathematicians usually refer them as morphisms. And again, the key concept is the compositionality of arrows. Here I drew a category with these four objects and some arrows between these objects. We also allow self-loop. And the composition of arrows is as you naturally expect. So if we have an arrow going this way, followed by an arrow going that way, then we should have an arrow going directly from here. Similarly, if we have an arrow going that way, followed by another arrow, then their composition is the arrow directly going there. So some examples. In logic, there's a category of propositions and proofs, where propositions are objects and proofs are the arrows between objects. And in computer science, there's a category of data types, and the arrows are programs. Similarly, in physics, so physical system as objects and processes as arrows. Now let's delve into our category theory approach to deep learning. Category theory has been successfully applied in structural modeling of quantum computing and natural language processing. And here is a recent paper on that, QNLP in practice, where QNLP stands for quantum natural language processing. And the recent applications utilize the framework of Dagger compact categories and the corresponding string diagram calculus. And actually, the people behind this project also developed a Python library called DiscoPy, which can implement these Dagger compact categories and string diagram calculus. So based upon the same method, we developed neural string diagrams, which is category theory for neural networks, as a compositional modeling language for deep learning and its categorical generalization. Therefore, we can use the already developed DiscoPy library to implement and compute our neural string diagrams. So in practice, neural string diagrams allow us to turn informal neural network architecture pictures into formally explainable, mathematically verifiable, and systematically composable entities in their own right. So for example, we have RNN up here, we have transformer, and we have CNN down here. So usually when we look at a neural network architecture, we see these kind of informal pictures to illustrate what's going on. But these are obviously not mathematically rigorous, and also different people might have different styles of illustrating neural network architectures. However, by turning them into neural string diagrams, we may then describe, compare, design, and compute different deep learning architectures in a generalized, mathematically rigorous fashion. Now let's move on to the technical framework of this project. Let me first introduce the string diagram. A string diagram is a directed graph consists of labeled strings and labeled boxes with specified input and output strings, together with certain notions of compositionality. So I drew some examples over here, and note that we always read the string diagram from left to right. So we have some string A, B, and C over here, and we have label boxes F and G with their input and output. And here's an example of a sequential composition. So if we think in terms of the category of sets, then F and G would be functions between sets A and B and C, and the sequential composition is just a usual sequential function composition. And here we have the parallel composition of the box F and the box H. So we can think of this in terms of the category of Hilbert spaces, and we would have the tensor product of linear transformations between A and B and the tensor product of C and D. And by considering objects as strings and morphisms as boxes, string diagrams provide graphical calculus for monoidal categories. And here are some more special morphisms that we're going to use later on. And a scalar lambda in a monoidal category is an endomorphism lambda from the unit object in the monoidal category to the unit object. And states are morphism that has the unit object as input, and the effects are morphisms that has the unit object as output. So we draw states in this way and effects in this way. And in monoidal category, the unit object is drawn as an empty diagram. So you can think of states as initializing, say, a state in a physical system A, or initializing an object in a data type of a data type A. And for effects, this is essentially discarding information. So we know something happened, then we don't care what happens after it. So for more information on string diagrams, I recommend this source, Introduction to Categorical Quantum Mechanics by Chris Cunin and Jamie Vickery. Now let me introduce the other part of the technical framework, the class of Dagger compact categories. So a Dagger compact category, first of all, is a compact closed category. Essentially, that means that for any object A, there exists a dual object A star. The primary example would be the category of finite dimensional vector spaces. As you know from linear algebra, for any finite dimensional vector space, there exists a dual vector space. Right. Secondly, a Dagger compact category is a symmetrical monoidal category. That means that for each pair of objects, the braiding morphism satisfies some string diagram equation. Right. So here I drew the string diagram for the braiding morphism. So braiding morphism is actually the thing in between. So that means that it just swaps the order of the tensor product or monoidal product. So to be symmetric monoidal, it means that the braiding twice gets you back the original input. So braiding twice is unbraiding. Right. So next, it has a Dagger structure, which is an involutive functor from the opposite category into the category itself, which acts on objects as identity and sends morphisms to the adjoints. So if you are familiar with quantum mechanics, this Dagger comes up quite a lot, but this is a generalization in terms of category theory. And the key example for Dagger compact category is the category of finite dimensional Hilbert spaces. For our purpose, we consider a subclass of Dagger compact categories, which are Dagger compact categories with biproducts. So a biproduct is both a product and a coproduct. And these kind of categories exhibit generalized vector space features. So first of all, it has a notion of a generalized basis for any object. So a generalized basis of an object is a unitary morphism. We denote it as B of A. That is it's a morphism from the n-fold byproduct of the unit object into A. Furthermore, to a morphism F from A to B, we can associate a generalized matrix that is M, which is equal to the basis of A, followed by F, then followed by the basis, Dagger version of the basis of B. And that is from the n-fold byproduct of the unit into m-fold byproduct of the unit. And you can actually prove that each entry of M is a scalar in terms of monoidal category. That is the endomorphism on unit object. So the analogy here in linear algebra would be to a linear transformation. We can associate a matrix. Right. Moreover, we use the suggestive notation Vn to denote a n-dimensional object. Furthermore, we use Vm times n to denote the internal Hom Vn Vm, which can be associated with a morphism F from Vn to Vm. So again, the analogy in linear algebra would be that Vm times n is the vector space of m by n matrices. Therefore, you can view each element as a morphism, a linear transformation from the corresponding vector spaces. Now, with the technical framework ready, we can introduce the neural string diagram for various deep learning architectures. The first one is CNN, and obviously the key component of CNN is convolution. And here we give the definition of convolution in Dagger compact category. And here is the string diagram for convolution morphism. So the convolution of type V n by n and Vk by L, where k is less or equal to m, L is less or equal to n, is defined as a morphism in such a way. So essentially you can think of this as the input and this as the filter space. So in particular, this is a very simple convolution that is just strike one and with no padding. But you can design more complex convolution as you wish. And for states A and B, the convoluted state A convolution B corresponds to a morphism in such a way. So in particular, the generalized matrix associated to the morphism A convoluted with B satisfies the following string diagram equation. Here, this part represents the ijth entry of the generalized matrix, and you can verify that this is how the filter traverses through the input. So to summarize, the definition of a convolution is, so if we get two states, A and B, and their convolution is this convoluted state, which is associated with a morphism, and again, it is associated with a generalized matrix. And here is the neural string diagram for a very simple convolutional neural network. It has one convolutional layer consists of two filters, F1 and F2. They're represented as fixed states. And we have some other morphisms. We have the copying morphism that duplicates the input, and we have the concatenation morphism, and we have some free nonlinear morphisms, ReLU, pooling, flatten, fully connected layer, softmax. And we're currently developing a two-level morphism system so that we can formalize these free nonlinear morphisms. And next up is the transformer neural network. Obviously, it relies on the attention mechanism. And here I drew the attention mechanism in neural string diagram. Notice that we have, again, the copying morphism, and we have generalized matrix multiplication and generalized matrix inner product. and the weight matrices are initialized again as fixed states. And then from here we'll get Q, K, and V matrices. Furthermore, we have the snake morphisms. So it's a composition of cup and cap. So cup and cap here are special kind of state and effect. It connects morphism that takes place in different steps. So with this notion of snake morphisms, we can introduce the notion of time flow. So not only we can read the string diagram from left to right, we can also read it through this snake morphism that connects different time steps. And finally, here's the full neural string diagram for a transformer neural network. As you can see, we got the positional encoding over here. We got an encoder, and it is connected via the snake morphism to the next decoder and further decoders. And this is the end of my presentation. Thank you for watching.